All right, everyone. This is going to continue your topic on redox. And in case you didn't read my post and you just clicked on the video, know that I forgot to do a chapter section from organics. So next week, I'm going to go back to organics, which means I'm going to try to summarize redox as best as I can today. However, I believe that your textbooks are supposed to be returned to your schools very soon, if not this week. And so follow the instructions, go back to the Google Classroom post and see what pictures you might want to take of the textbook before returning it. I think it's very valuable that you will cover both this week's topic and what I am going to ask you to do for next week. They are all just ways to prepare you for university, as you can see in my title here. Okay, I am not going to be able to cover fully chapter 9.3. I think it's going to be a bit overwhelming, but if you feel like you can handle it, please read it. I'm going to allude to what you may or may not be missing if you don't do chapter 9.3. Okay, so let's get started. Balancing redox reactions. Going back to this new system of looking at molecules, not by electrons, but by these redox reactions, not by filling the outer shell or the valence charge of these in the periodic table. There's a reason for it. And in doing so, I think it's best if I just demonstrate by doing some sample questions straight from the textbook. The textbook asks you to balance this reaction. So that is nitric acid plus solid copper gives me nitrogen dioxide plus copper nitrate, aqueous, and water. So without actually going into redox reactions or that topic of, pause the video and I challenge you, try to balance this with 100% confidence. Try to balance it. Assuming you tried it and you're playing the video because you failed, I would expect you to fail. Now, the main problem is up until the grade 11 period, grade 11, I guess, level, you always had some kind of metal and some non-metal, or rather a cation and an anion. And here, obviously, as a metal, it's going to become a cation. So you do a single displacement reaction. But take a look. This was never a part of the reactants. Here is my anion from the reactants. Here is the cation from the metal. And where did water come from? Right? It typically, if you did this correctly, you would have had H2 and you've gone to balance it. But the fact of the matter is, in reality, the world does not, I guess, behave just on single displacement, double displacement, synthesis, decomposition, and combustion. It doesn't. These reactions do happen, and this reaction cannot be explained by the conventional means that you learn in grade 11. So how do you do it? And that is where redox comes in. So here is something you can't balance and put in the coefficients just easily. So we start by talking about redox reactions, and we try to narrow down where the electrons come from and where do they go. That will give us a better idea of how many molecules of HNO3 and how many molecules of Cu are needed. Here we go. Using redox numbers, I know that oxygen is always going to be -2. I have 3 oxygens, so total that's going to be -6. Okay? Hydrogen typically is going to be +1. And I only have 1 of them, so it's going to be +1. That means my nitrogen must have a redox or oxidation number of +5. Let's move on. Copper, being an element, it's going to have an oxidation number of 0. Oxygen, again, -2. That means it's a -4. That means nitrogen is going to be a +4. Here, oxygen is a -2. That's going to be -6. That means nitrogen here must be a +6. Oh, sorry. From there, it's probably better to actually take a look at this. This is going to be a -6 here. However, the entire nitrate, needs to have a charge of -1. So if I want nitrate NO3 to have a total charge of -1, then nitrogen must be +5, and copper will be +2, because, you know, -1, -1, I have 2 nitrates. Water, I don't think I need to worry too much about it. Oxygen being -2, hydrogen is going to be +1 each, which means it's going to be +2 altogether. That's going to be +5, and that is a +2. Okay, so let's, using some different colors, I'm going to try to highlight exactly where the electrons went. Take a look. Nitrogen had a oxidation number +5, and it has a +5 here. So there's no difference in that. No electrons moved. As you can see, this is nitrate, and that's nitrate. We don't have to worry too much. Here it's where it gets a little funky. Nitrogen here is a +4. It used to be a +5. It became a +4. What does that mean? Is this a reduction or an oxidation? Going once, going twice. This is a reduction. And I gained 1 electron. Okay, the number was reduced and I gained 1 electron. Okay, let's talk about oxidation. Well, if it gained an electron, that means something must have also lost in a sense. We have copper with an oxidation number of 0. Copper has an oxidation number of +2. The number went up, which means that is an oxidation. Oxidation, I can't spell. And I lost 2 electrons. So we know where the chemical change is occurring in this reaction. And of course, water, hydrogen +1. So I'll use black. Hydrogen is a +1, that's a +1. Oxygen is a -2, -2, -2, and -2. There's no change. The red and the blue are where the changes are happening. This is a chemical reaction. So are we done? How do we use this information to balance? Well, again, we're balancing. If you remember, back in grade 11, you balance chemical equations based on the number of atoms, of course, because of conservation of mass. And there's also a conservation of charge. Whatever charge is on the left side has to equal the charge on the right side. If I gained 1 electron and I lost 2 electrons, there is not a balance in charge. But according to this equation, there should be. What does that mean? For this thing to lose 2 electrons, that means this nitrogen must have gained 2 electrons. In other words, I need 2 of these and 2 of these. Maybe I could do that using the red. I need 2 of these and 2 of these so that the single electron that's gained is going to be multiplied by 2. So I have gained 2 electrons. Now it is balanced. And that is essentially the bread and butter of balancing redox reactions. The reason why you've been practicing so hard and trying to figure out the oxidation numbers from last week was because you're going to be using them a lot this week. Okay, a couple of things to note. There are situations that slightly change if you are doing this reaction in an acidic condition or in a basic condition, but we'll get to that in the second problem set. Okay, so here it is. Now that we have this coefficient of 2, 1, 2, 1, and 1, we're going to take a look at whether we have truly balanced this equation or not. Let's count how many of each atom or element that we have. 2 hydrogens, 2 hydrogens, 3 oxygens, 4 oxygens, sorry, 6 oxygens here, 2 and 6, whoa, and 7. Sorry, 2, so it's 4, 5, 6, so 10, 11 oxygens. That's not going to help us very much. So how do we go about balancing that? Take a second and look around the rest of the equation. You are going to be eyeballing this to figure it out. Take note, the nitrogen from here, remember, gained 1 electron and became nitrogen dioxide. So these two molecules, these two nitric acid molecules became or were used to become nitrogen dioxide. But we still have two molecules of nitrate here, two ions of nitrate here, which means I need more than two. I actually need, let's erase this. I don't need two, I need four. Two of them is going to go and just remain as nitrate, and two of them will become nitrogen dioxide. Okay, so with that, I think that might help us with our balancing of oxygens. We have 12 oxygens here. Again, 4 right, plus 6, that's 10. Ooh, 11, not balanced. Luckily, I noticed that because I increased the coefficient of the nitric acid, I have 4 hydrogens, which means I need 2 molecules of water to account for the 4 hydrogens. Now let's look at the oxygens. 12, 4 plus 6 plus 2, I think we're good. The coefficient is 4 to 1 to 2 to 1 to 2. That's it. So that might have been a bit of a handful. I intentionally went a little bit slow. How about we try the next one? Once again, you're gonna see another example of a redox reaction. You're gonna be balancing, but sample problem 2 from the textbook, that's page 610, is going to be done in an acidic environment. Okay, and you'll see that happen. Clearing the screen in 3, 2, 1. All right, let's do this. This reaction is going to be between ferrous ion turning me into a manganese ion, aqueous, plus Fe3 plus aqueous. All right, and this has a charge of -1. This is going to be in an acidic environment. So let's take a look. First things first, I have no idea where the oxygen went. It doesn't make any sense, doesn't it? Grade 11 won't be able to solve that. But we are going to approach this in a redox way. So this is going to be a charge of -2, sorry, an oxidation number of -2, which means this as a total is -8. If the overall molecule has a charge of -1, that means my manganese must be +7. Let's keep going. Oops, +7. Let's keep going. Iron, +2. I think that gives it away. Manganese, +2. I think that gave it away. And the iron is +3. I think that gave it away. Okay. Iron looks like the number went up. That is an oxidation. And it lost 1 electron. Okay? Whereas manganese, wow, it gained 5 electrons. In other words, it's a reduction. Well, already starting to see things. 5 electrons versus 1 electron. And so if I want to balance the amount of electrons that actually moved, we would have to say that there were 5 iron ions, which turned into 5 iron ions. Okay, ferrous to ferric. So this would be times 5, which is 5 electrons. We are happy. From here, we move on to eyeball to make sure, I eyeball the equation to make sure they are fully balanced. 1 manganese, 1 manganese, 5 irons, 5 irons, 4 oxygens, no oxygens. Times like this, because we're in an aqueous situation, we can harmlessly pretend that there is a production of water without changing anything to the reaction. And so we say there's 4 water molecules to account for 4 oxygen atoms, which means I added 4 oxygens, yay, but I also added 8 hydrogens. Where's that going to go? This is why it makes sense to say that it's in an acidic environment. We say in the reactant side, there are 8 hydrogen ions. Again, this is okay for us to add in because the question said we were in an acidic environment, and this would tell us that, yeah, there are more hydrogen ions. It is, it behaviors, or the pH value would be something, okay? There's more hydrogen ions than hydroxide ions. And so it's acidic. We're good. And have we balanced it? Let's take a look to make sure that there's 1. There is a, let's see, 1 manganese. We have a charge of -1 here, a charge of +10 here, and a charge of +8 here. So total, the overall charge is +17. We have +2 from the manganese, +15 from the iron, and nothing from the water. Together, that is a charge of 17. So the charges balance out. 1 manganese, 1 manganese, 5 iron, 5 iron, 8 hydrogen, 8 hydrogen, 4 oxygen, 4 oxygen. The atoms balance out as well. I think we're good. If you want to know what changes when we are doing it in a basic environment, take a look at problem sample question number 3. And that essentially what you're doing is when you have an imbalance of a hydrogen or an oxygen, you're basically not adding water, but you're just adding hydroxide ions. That's the only difference between being in an acidic versus a basic environment. Okay? From here, I'm going to ask you to just stop the video and you can continue working from the textbook. I'd like you to try numbers 1 to 3. Oh, sorry, 1 to 6. That should give you extensive practice. The textbook also asks you to learn a different method of solving an equation. It's called the half reactions method. And it works. You're totally free to try it and explore it. It's on page 614. And further practice would be page 617, numbers, I think 2, 3, 6, and 7 will be pretty good for you. Okay, you can pause the video, you can stop here, because I'm actually going to clear the screen and talk a little bit about 9.3 and what you may want to, I guess, prepare yourself for if you're continuing chemistry in university. I'm going to clear in 3, 2, 1. I'm going to actually go back to that previous reaction that we just did. That's sample question 2. It's MnO4 minus. I'm leaving out the aqueous. I hope that you can just mentally know that aqueous is there. So if you remember, there was a big challenge in grade 12 where you were learning about enthalpy and a spontaneous reaction. And if you remember, typically spontaneous reactions were when the overall enthalpy was negative, right? Or if I were doing it as a potential energy diagram, it was like this. If you're able to overcome the activation energy, this is your delta H, right? So my question to you, back to redox, is how do you know it's going to go in this direction only? How do you know, or what if the equation was written separately or reversed? Would you have questioned me? Well, after your study of the of heat, enthalpy, and that entire unit, you should have, and also in equilibrium, a little bell should have rung in your head saying, what if, right? And if you were to ask that question, good job. The answer is, the only way you can tell whether it's going to be in the forward direction or in the reverse direction, is by checking which one of these wants to be the greater oxidizing agent, or which one of them is going to be a greater reducing agent. Okay, so when it comes to redox reactions, we're going to take a look at how strongly one agent wants to oxidize another. Okay, and that will be seen in a kind of chart. So again, going back to chapter 9.3, one of these, so manganese, if I remember from the previous reaction, that was going to be a reduction. Right? And iron was oxidized. What that means is iron, Fe2, to Fe3 plus is a stronger reducer or reducing agent than manganese. Right? And you can only figure that out by actually using a chart. You will see a chart full of these things called EV when you look at the data table that we use all throughout this year. If you go to page 620, it alludes to this thing called a redox table. That's just like a table of enthalpies. And you take a look at which one is more readily releasing energy than another. That's all it is. There's not enough for me to just tell you everything in a video. It's more better. I think it's better if you go ahead and explore it. And this will continue on, and you will learn how to use it in chapter 10. But again, because of our situation, we don't really have an opportunity to get into chapter 10. It hurts me to say, but you will have to study it carefully or look on resources online next year. I don't think they're going to throw this at you in university just because, you know, they expect you to know it. They will sort of teach you all over again. But the amount of time that you get in learning it and absorbing it will definitely be shorter compared to what you had in high school, right? Because university, it's like, hey, if you keep up, you keep up. If you can't, then leave. It's a bit of a dog-eat-dog world, especially in the science world. So do your best. If you have the time, take a look and sort of gloss over chapter 10 and see what you can absorb from it. Chapter 10.1, 10.2 is enough. It talks a lot about electron transfer and how that can in turn be used in the world of physics and electricity. So some of you who've been doing physics, you might find that familiar. Okay, best of luck. Honestly, you know what? I'll leave it at that. Best of luck, everyone. Next week, I am going to touch a little bit on chapter 1.7. That's amines and amides. So stay tuned. And with that said, if I don't see you or hear from you, then I do hope that you have a good summer. Keep yourself safe and really enjoy, because it looks like we're slowly, ever so slowly, opening up the city again. See you soon.